Thank you for coming to our second monthly Astrobiology Colloquia. We're really excited to have Kristin here with us today from the Applied Physics Laboratory. You know, every once in a while you come across professionals who have had a circuitous route towards what they're doing today. And in my mind and in my experience, it always makes them much more interesting, especially when that circuitous route gives them different perspectives or different expertise or interdisciplinarity. And I think Kristin has all of those things. She started out in, applied physics, right? But worked on instruments and systems engineering, still does at APL. But at a later stage in her life, decided she wanted to go out and get a PhD in astrophysics. And met with a lot of resistance from people who said, that's a terrible idea. You shouldn't do that. That's going to be too hard. But she did it anyway. And so I think that gives her just a lot of really interesting expertise and perspectives. And I'm sure that that will shine through in her talk. So thank you again for coming and having me here.
Thank you, Natalie, and thank you everyone for the opportunity to speak with you today. So the title of my talk is Bridging Worlds, Exploring Titan and Exoplanets in the Quest for Astrobiological Insights. And some of you might be thinking, Titan and exoplanets, those are different things. Of course, you're right. But as someone who has worked on both planetary missions and now moving into exoplanet research, I think that I found that there are valuable opportunities in both solar system science and in exoplanet research that have a lot to bring to bear for each other and for an interdisciplinary field like astrobiology. So from the astrobiology perspective, astrobiology revolves around a few key questions, some of which are how life began and evolved on Earth and how could it evolve on another world, whether life exists elsewhere in the universe, and how we search for and identify that life. So today, I want to focus on two of these questions, and all three of these questions have an array of subtopics that tie into them to build up that we will eventually use to build up the answers to those questions. So today, I'll focus on the questions of how life began and evolved, and more specifically, the timelines and processes for prebiotic chemistry and how we want to use the Dragonfly mission to start to address and constrain that question a bit. And then given the exoplanet data that's been coming in over the last decade, and of course very recently with JWST, I wanted to also talk about what is the probability of a given world being habitable. And for that question, I'll talk specifically about one of the JWST observing programs that I've been involved in, as well as one of the ICAR programs. Before I jump into any more detail, I do want to call out that the work that I'm presenting today is the condensation of the work of lots of people. The JWST and ICAR programs are composed of dozens of scientists from various institutions across the world. And the Dragonfly mission, of course, is a team or has a team of hundreds of scientists and engineers that have been doing a lot of work on this program for years. So what I'm presenting today is just a small representation of the work done by those people. Okay, so starting with Dragonfly, some of you might be wondering, okay, why Titan? Isn't it just kind of a cold moon orbiting Saturn, like far away? Yes, but Titan is a unique place, it provides a unique environment that has the opportunity for some very compelling science. For Earth, even for Earth, we don't really know how life came to form on Earth. We have maybe some ideas of the prebiotic chemistry processes that occurred, but the evidence for the processes that led through prebiotic chemistry into biochemistry have largely been erased from Earth's surface or inaccessible through tectonic, geologic, and weathering processes. But Titan is one of the places in the solar system that is the most like the early Earth. And we think that there are places on Titan where there may be opportunities. There may have been opportunities in the past for some prebiotic chemistry to possibly have occurred. And we hope that on Titan that those processes have been reserved in accessible places on Titan's surface. Titan is the second largest moon in the solar system behind Ganymede. It has a surface gravity 1/7 that of Earth's, so just a little less than our own moons. And Titan is very cold. It has a surface temperature of 94 Kelvin, which sounds very inhospitable for humans. But that doesn't mean that there aren't places on Titan where certain chemical processes could have occurred. We think that the indications are that the bedrock composition on Titan is water ice, and because it's so cold, Titan's has been able to retain a very dense atmosphere. So the surface pressure on Titan is actually half again the surface pressure that we feel on Earth. And that atmosphere is primarily nitrogen with a few percent methane. And that methane in Titan's atmosphere is one of the things that makes Titan such an interesting place, because the photochemistry in the upper atmosphere produces complex carbon molecules. So the methane and the nitrogen in the upper atmosphere encounter the UV and energetic particles from the sun, and they form organic compounds that aggregate and drift down to Titan's surface. So Titan has a wealth of organic material on its surface. And also, through a couple potential mechanisms that I'll talk about in a little bit, we think that there has been a potential for those compounds, for those organic compounds, to have mixed with liquid water on Titan's surface. So Titan is potentially a singular destination for understanding the chemical processes that occurred on our own planet that supported the development of life in a somewhat Earth-like context. So most of the exploration of the Saturnian system has been by probe. So we had the Pioneer 11, Voyager 1, Voyager 2 flybys in the late 70s and early 80s. And then, of course, we had the Cassini mission that operated from 2004 to 2017. And the Cassini probe delivered the Huygens probe to Titan, which landed on Titan in January of 2005. And all of our in situ data for Titan come from Huygens. So it's descent through the atmosphere and then a couple hours of operation on the surface. And other than that, all of our data for Titan come from Earth and space-based telescopes and Cassini and a few measurements from the Voyager and Pioneer missions. Here you can see a map of Titan's surface in the near infrared and infrared wavelengths from the visual and infrared mapping spectrometer. And there are a couple of things that I want to point out here. The bluish colors that we see kind of scattered around are interpreted to be areas that are rich in water ice. So we can see even from Cassini's flybys that there are some significant areas that we would expect to have water ice bedrock. And then we have these lighter areas in the upper latitudes that are interpreted as highlands. And then along the equator, for most of the equator, we see this belt of darker material that we think are complex hydrocarbons. And for most of that belt, what we actually see from the Cassini radar data is that these hydrocarbons have formed dune-like structures. And these are large dunes. They're about 100 meters tall and 1 to 2 kilometers wide, and a couple kilometers apart. And you can see from these images that they're very long and that they kind of flow around these other bedrock type structures that we see on Titan. Titan we've also observed clouds and weather patterns on Titan. And this is because that similar to how Earth is at water's triple point, where it can be a solid, liquid, or a gas, depending on minor temperature fluctuations. Titan's temperature and pressure is such that methane can be either liquid on the surface, or it can evaporate, form clouds, and precipitate back down. So Titan has a methane cycle very similar to Earth's water cycle. And we have indications that methane cycle has shaped Titan's topography in ways that look very similar to the way that water has shaped topography on Earth. We see the polar lakes and seas in the high northern latitudes. And we also see these channels, these branching channels that look very much like river flows that we see on Earth. So we don't know when the last time there were heavy rains on Titan, but we do think that that the methane has precipitated on Titan in flows that can shape the topography and carry materials and distribute them over Titan's surface. And the other thing that you may have noticed when I showed the map before are these things that look like impact craters. And we have multiple structures that we have identified as these craters. And impact craters are of particular interest because obviously when an impactor strikes the surface, it will warm that surface. And when that surface is made of water ice, the ice melts and becomes liquid water. And if there are complex organics on that surface, that gives that chance for water and organics. And depending on the nature of the impactor, that water could stay liquid for, we think, on the order of tens of thousands of years. So in the lab, we have shown that if you take tholins and other complex organics, like what we expect to see on Titan, and put them in liquid water for on the order of hours or days, you can start to form amino acids and sugars and those kinds of things. So if Titan had a chance for there to be those types of compounds mixing in liquid water for tens of thousands of years, then maybe some of that type of prebiotic chemistry could have occurred on Titan. So Titan has the key ingredients necessary for life as we know it. It has energy coming from the sunlight and the photochemistry. It has abundant organic material coming down through the atmosphere, and it has two liquids. Water, either from impact melt or possibly the interior ocean, or maybe cryovolcanism. And it also has that liquid methane that engages in that active methane cycle. So on Titan, we can study prebiotic chemistry in the context of a planetary environment with Earth-like surface processes. Titan, therefore, offers the opportunity to take the next steps in answering the questions of what makes a world habitable, what chemical processes led to the development of life, and whether life has developed elsewhere in the solar system. But to really take advantage of these opportunities that Titan has to offer, we need to go there and get more in situ measurements. And that is what NASA's Dragonfly mission aims to do. Since the atmospheric density on Titan is so much greater than that on Earth, and the gravity is so much lower, heavier than air mobility is actually very efficient on Titan. So the Dragonfly lander is designed to exploit that efficiency in the form of a rotorcraft lander that can be relocated to multiple different landing sites. The Dragonfly mission comprises a couple of different elements. We have our Cruz stage, which will, in our entry vehicle, which will get us to Titan. The entry, descent, and landing assembly will get the lander safely through the upper portion of the atmosphere. And then, of course, the heart of the mission is our rotorcraft lander. And you can see here a photo of our PI, Dr. Ziggy Turtle, who is holding a model of one of the rotors to give you a sense of scale for how big the lander is. So it's basically the size of a small car, is what we're looking at. So the advantage of the relocatable lander is that we can take the entire payload, all of the instruments, to different locations on Titan. We don't have an orbiter, so we do have to use direct Earth communication. So you can see that with we'll primarily use our high gain antenna here, communicate with Earth. And Dragonfly's primary battery or primary power source will be its multi-mission radioisotope thermal generator, MMRTG. And that will charge our onboard battery, which will be used to power flight activities, science activities, and our data transmission. And as I mentioned earlier, Titan's very cold. We do have some systems that need to be kept warm-ish. But the great thing about the MMRTG is we can use the waste heat coming off the MMRTG to maintain a nominal thermal environment in the interior of the lander for those systems that need to be kept warmer. So Dragonfly is aiming to accomplish a few science goals. As I mentioned, one of the big things we really want to look into is this question of the prebiotic chemistry and looking at the structure and components of the regolith on Titan's surface. And we also want to learn more about the makeup and structure of the subsurface of the bedrock to get an idea of if that mixing occurred, what some of that chemistry was. We'll also investigate Dragonfly in the context of habitable environments by taking measurements of the atmosphere conditions and looking to see if we can identify methane reservoirs and determine methane transport rates. And we also have a measurement that will potentially provide, is essentially looking for biosignatures to look for indications of potential metabolism or.
What did you mean by methane reservoir?
So Titan actually, the photochemistry in the upper atmosphere is such that the methane, either between being broken up and hydrogen escaping or the methane forming the compounds, the methane, based on the abundance in the current abundance in the atmosphere, should have been gone by now. So we're not actually sure what is replenishing the methane in Titan's atmosphere. So one of the things that we want to do with Dragonfly, one of the measurements that we're taking is a methane abundance measurement to see if we can detect changes in the methane abundance as we're transporting.
Are you thinking about like outgassing or pools or?
There are all kinds of different theories.
It's a wild card. Okay.
Yeah. So subsurface pockets of various different structures, and that kind of thing. So Dragonfly has 5 different instruments. We have our mass spectrometer, which we call DRAMS, the drill for acquisition of complex organics, Draco, which is our sample acquisition system that feeds the mass spectrometer. We have our geophysics and meteorology package, DRAGMET, and that's the instrument for which I am the instrument scientist and systems engineer. We have our camera suite, DragonCam, and our gamma ray and neutron spectrometer that we call Dragons. So the mass spectrometer is going to provide data that we can use to analyze the chemical components and processes that have occurred on Titan, hopefully providing indications of some of that prebiotic chemistry. And our mass spec is capable of both laser desorption of mass spectrometry and gas chromatography. So the laser desorption can provide a broad analysis and a broad survey and structural analysis of the components in the regolith, whereas the gas chromatography will provide more definitive molecular structures of detection. It also allows to look for chirality, which, as we know, is one indication of life or life-like chemistry. Our dragons, our neutron spectrometer, will measure the bulk elemental composition of the regolith and the local subsurface so that we can kind of broadly classify the bedrock that we're sitting on and look for minor inorganic elements. So essentially giving us an idea of, are we sitting on pure water ice, or are there some salts or minerals mixed in there? And it will also give us an idea of the near surface stratigraphy. The geophysics and meteorology package is composed of 12 different types of sensors that will take a plethora of measurements. So we'll measure the temperature and pressure of the atmosphere, both, and most of these measurements are taken, or many of these measurements, I should say, are taken both on the ground and during our flights. So we'll measure the temperature, the pressure, the methane abundance, and the hydrogen abundance. And then on the surface, we'll measure the wind speed and direction. We also have sets of sensors on the skids that will be in direct contact with the regolith so that we can measure the dielectric constant and the thermal properties to get an idea of kind of broad material categorization, porosity, and the thermal response of the regolith, which will give us an idea of how damp it is, and therefore be an indication of whether we might want to collect a sample in that particular location. Dragnet will also look for seismic activity using 2 sets of geophones and a deployable seismometer. And we'll use a couple of antennas to look for indications of the Schumann resonance that may have been detected by Huygens, which we can use to help constrain the thickness of the ice crust. Dragon Cam has multiple different cameras that are located to take pictures of in front, underneath, and on the sides of the lander. And we also have a microscopic imager that will take kind of more close-up, higher resolution images directly of the site that we'll be drilling, so that we can get a good sense of what regolith we're collecting by the drill. So we can use the pictures from, or the images from the sides and front of the lander to place the other measurements that Dragonfly is taking in a geologic context. DragonCam will also include an LED array with LEDs in multiple wavelengths, as well as UV wavelengths, since aromatic compounds and especially PAHs fluoresce when stimulated by UV. So as I mentioned, impact craters are potentially very interesting. So Dragonfly's destination of opportunity is going to be Selk crater, which is located a little north of the equator on Titan. And it's also located near some of those dune fields that I mentioned. So Dragonfly is aiming to land in the dune fields just south of Selk crater, and then work its way north to the crater itself. So the nominal Dragonfly mission duration is a little less than 3.5 years. And so we will cover the distance to Selk crater, which, depending on where we land in the ellipse, is, call it roughly 150 some odd kilometers. And so we'll cover that distance to the crater in, we estimate, about 74 T-sols or Titan days, where a Titan day is 16 Earth days. So each relocation flight will cover a few kilometers at a time, and that will allow us to explore, we estimate, at least 30 unique sites on Titan. And the flights themselves are only on the order of an hour or so. So we're actually going to spend the vast majority of our time on Titan's surface, taking science measurements, and then during the Titan day, and then during Titan night, since we can't communicate with Earth because it will be below the horizon. The lander, most of the systems for the lander will actually go into a hibernation to allow the battery to charge, except for some of the Dragnet sensors, because we're special. So Dragonfly is currently in phase B. Our systems and mission all passed our PDRs in late 2022 and earlier this year. So we're currently conducting subsystem and instrument testing, prototype testing, and engineering model development and builds, as well as model validation. And we're using some of APL's test facilities as well as test facilities at other locations to do that hardware testing. Since Dragonfly's flight activities will all have to be autonomous because Saturn is a 70 to 90 minute one-way 70 to 90 minute light time delay. Yeah, that's what I was saying. Dragonfly effectively has to fly itself. So our mobility team has been hard at work developing the algorithms to allow Dragonfly to do that. And they have demonstrated the guidance and control algorithms, the optical navigation, and autonomous takeoff, cover, landing, and scouting flights. And here you can see some of the photos from testing they've done out at Lima. We do have a model and other cool images and videos and things posted on our website at dragonfly.jhupl.edu. So if you want to see cool images, I would send you there. And I would like to show this video, which I misplayed. Yes. So this is a video showing the concept of Dragonfly's initial landing, flight and landing. So it detaches from the aeroshell and then flies probably a few kilometers. And it will locate a safe landing site, which we hope looks that nice and clean. And then it will deploy the high gain antenna for communication with Earth. And then once we're done with the surface commissioning phase and ready to relocate, we'll deploy or stow the antenna and find a spot to land. So that's going to wrap up the Dragonfly portion of the talk. But again, I would send you to our website if you want to find out more. Okay, so going back to our central questions that we're looking at today, we'll move on to the question of whether life exists elsewhere in the universe. And one of the topics or questions that is facing us right now in the wealth of exoplanet detection, in the face of the wealth of exoplanet detections that we have, what is the probability of a given world being habitable? All right, so an extrasolar planet or exoplanet is a planet orbiting a star other than the sun. And the first exoplanets were discovered in the early to mid 1990s. And we can see from the chart on the right that the detection rate was fairly slow in the beginning and relegated primarily to large planets orbiting very close to their stars, what we call hot Jupiters. So then, about a decade ago, thanks largely to the Kepler and TESS space telescopes, the number of exoplanet detections effectively exploded. Went no-go, as it were. Sorry. And you can see from that chart on the right that most of the vast majority of these planets that we detected are transiting. From the graph on the left, we can see that as of, I don't know, a couple weeks ago, there were over 5,500 confirmed exoplanets. And the thing that I find really interesting personally myself is that most of those planets, about 2/3 of them, are either are Neptune-like and smaller, and that about 1/3 of them are expected to be rock, to be super Earths or terrestrial. And to me, that's a really important statistic because to look for life as we know it, we're going to want to look at these rocky worlds. And from the Kepler and TESS orreries, we can see that exoplanets present a wide variety of planet and system and star combinations. And from those statistics and detailed studies, we can get information on the processes that shape planetary formation and evolution, the star-planet interactions and how that shapes planetary evolution and planetary atmospheres over time. And it also will provide context for the past, present, and future of Earth and the other planets in our solar system. More specifically to astrobiology, there have been a few historical attempts to try to estimate the number of planets that might have life or that might have intelligent life. And I'm sure many people in this room are familiar with the Drake and Seeger equations. The Drake equation being formulated in the 1960s to try to estimate the number of intelligent civilizations present in the galaxy at any given time. And the Seeger equation being a tweak on that to estimate the number of detectable inhabited planets. And until we started getting these exoplanet data, the only variables in these equations that we could really estimate were the variables pertaining to the stars. We didn't have any idea of whether other stars had planets, how many of those stars might have how many planets, whether those planets had atmospheres, could be hospitable for life, etc. But now with the exoplanet data that we have, we can start to put constraints on these parameters. And one of the big questions right now is, okay, we've detected all these exoplanets, but how many of them actually have atmospheres? And one of the reasons we care about that question is because we don't want to point a telescope for which the time is, resource constrained and competitive at a planet and just throw a dart at the wall and pick a planet and essentially get an expensive flat line because that planet doesn't have an atmosphere. So if we had a way of determining essentially a probability of whether a planet has an atmosphere and therefore kind of fulfills one of those first criteria of whether we should go look at it in more detail, is one of the questions that we're trying to address today. And one of the trends that we see in the solar system is this sort of division between worlds that have atmospheres and worlds that don't. And this, for our solar system, it seems to be a function of the insolation relative, which we usually express relative to the Earth, and that world's escape velocity. So one of the questions is this solar system trend borne out in the general exoplanet population? And this is this trend of the division between planets with atmospheres and planets without atmospheres is termed the cosmic shoreline. So the JWST program that I'm involved in, and several others, as well as the CHAMPS ICAR, CHAMPS being the consortium on habitability and atmospheres of indoor planets, are looking to start answering some of these questions. So we have the question of whether JWST can distinguish planetary features from stellar inhomogeneities, because the transit light source effect has become something of a point of discussion within the community. And then we have the question of which M-dwarf planets have atmospheres, and M-dwarf planets provide good targets just because of the signal noise of an Earth-sized planet relative to the smaller star. And then for M-dwarf planets that have atmospheres, does the prevalence of atmospheres correlate with that solar system trend that we observe? So as I mentioned, there are several JWST programs that are kind of poking at this cosmic shoreline question. And you can see, and the colored, the circles that are colored in represent targets for JWST that either planned or have been observed already. And so and this yellow band represents the notional cosmic shoreline measure. Where on the lower right side is where we would expect to see planets that are less likely to have atmospheres, and the upper left being planets more likely to have atmospheres. So since most of, as per the graph I showed earlier, since most planets are transiting, and our primary tool for studying the atmospheres of these planets is transmission spectroscopy. So I'll just walk through the basics of that real quick, in case anybody's not familiar. So when we talk about a planet transiting, we're looking for the periodic dimming of the star's light as the planet passes in front of it. And that dimming that we see, that decrease in the flux, is called the transit depth. And that's a function of the ratio of the planet to the function of the ratio of the radius of the planet to the radius of the star. So a bare rock will produce the same transit depth in all wavelengths. So that's where we get our flat lines. But if that planet has an atmosphere, the gases in the atmosphere will preferentially absorb the star's light at different wavelengths, depending on what gases there are. And from that, we can construct a transit depth as a function of wavelength, which gives us our absorption or transmission spectrum. So I will note that a planet with a cloud deck is because the clouds will block most of the star's light equally in all wavelengths or most wavelengths. A planet with a cloud deck is indistinguishable from a bare rock of the same size. So if we see those expensive flat lines, it is possible that the planet has an atmosphere and just has a cloud deck that we can't see. So this is what our transmission spectra look like. And the main thing that I want to point out here is that our increasing y-axis indicates more absorption and therefore less light. So what we're looking for are these peaks. And so like for this spectrum for WASP 39b, we can see some CO2 and some water and a couple other things. So going back to our M-dwarf cosmic shoreline plot, these are the targets for JWST General Observing Program 1981, which is a program I've been involved in. So we have a couple targets further away from that division that we wouldn't expect to have atmospheres, or at least thick atmospheres, and then a couple sort of on the edge, and then TRAPPIST 1H kind of straddles that cosmic shoreline. So going into some of our results. So for our first planet, LHS 475b, you can see here our JWST data, which initially on first glance, there's not a lot that pops out there. But having done a fit to a couple different, or to multiple different atmospheric models, we were able to rule out low mean molecular weight atmospheres, so it's not hydrogen. And we found that a CO2 atmosphere, which is a high mean molecular weight, actually provides an okay fit to the data. But the data are also not inconsistent with a flat line. So at this point, with 2 transits of this planet, we could interpret the spectrum either way.
So, broad question.
Yeah.
About GWC spectra like this. Are the errors in nearby wavelength channels independent of each other, or is there some correlation in error between nearby wavelength channels? Like, how white should I think of the noise as being?
That is something we check for, and for NearSpec, which is the instrument that most of our planets have been observed with. We have found thus far the noise to be fairly white.
Good.
We did find some correlated noise with NearCam. So that actually, I'll talk about that. Okay. Okay, so then we got our observations of the super Earth GJ486b. And you can see in the black here are NearSpec data. And we found that these data were most consistent with a water-rich atmosphere, which sounds very exciting. A water-rich atmosphere on an Earth-like planet in orbiting an M4 star. Very cool, right? But wait. So this is, I mentioned earlier, the transit light source effect, and this was something that we checked for GJ486b. And so what we're seeing with the transit light source effect is that we get an estimate of the star's spectrum by observing the out of transit, the star when the by observing the star when the planet is not transiting. So notionally getting a spectrum of just the star itself. But what we're really getting is a disk averaged spectrum of the star. But the light that's coming through the planet's atmosphere is actually coming from just a cord of the star that the planet is crossing in front of. So the disk average spectrum for the star may not actually be representative of the light that's coming through the planet's atmosphere. And with M dwarfs in particular, if there are unocculted star spots that we're seeing in that spectrum, the water that we're detecting may actually be in those star spots, and therefore the water could be stellar contamination. So we did something of a check against that. And for the wavelengths for which we have data, for those NearSpec wavelengths, a water-rich atmosphere or stellar contamination could explain the spectrum that we're seeing, with maybe a slight edge to the water-rich atmosphere, but not enough to say anything definitively. So really what we need is measurements in the shorter wavelengths where we see greater differences between the star spot contamination, the spectrum from the star spot contamination and the natural atmosphere. Our third target was GJ1132b, which was a bit of a contentious planet before JWST, just based on some Hubble data, because we had one study, Swain et al. 2021, that claimed to find HCN in 1132b's atmosphere, but a couple other studies done a little later looked at the same data and just reduced it a little differently, and they found no indications of an atmosphere. So different reductions of the same data can lead to different conclusions about the same planet. And that's something I'll actually talk about again for our next period. So we looked at this planet with JWST using 2 transits with NearSpec, and unfortunately, this winds up being another demonstration of why you should never measure something only twice, because our two visits are also in conflict with each other. So from our first visit, we see what looks like an absorption feature near 4.5 microns that we don't see in the second visit. And this was using the same data reduction processes and analysis and statistical tests. And we don't think this is due to planetary variability. It's possible that it's due to some kind of instrument systematics, or maybe the 4.5 micron bump is actually some kind of random noise that we couldn't correct for. But really, the key takeaway from this target is that there are risks to claiming definitive atmospheric detections from single JWST observations. So moving on to GJ 341b. So this was the one that we observed at near camp. So we have a spectrum that we can see, and we used 3 different data reduction pipelines on the same data. And you can see here that the results from the 3 reductions are very similar if you look at just looking by eye. But if we put each of those reductions through an atmospheric retrieval process, we get very different interpretations. And a big reason for this is that GJ341b it's the smallest and coolest planet that we've looked at so far in this program. And so that means that the atmospheric scale height and therefore the spectral features are going to be very small. So even with our high precision JWST data, those slight variations in the reduction that we get from different pipelines lead to a non-conclusive atmosphere detection, whereas in the Tiberius reduction pipeline thinks that there is a lot of CO2 and not very much ozone, whereas the T-SWIFT pipeline thinks that there's not really any CO2 and that there is ozone. So
The reductions here, the 3 reductions don't look as similar as they did in the previous slide, though.
that might be because of the binning.
Oh, well, maybe they are.
So I think it's still hard to tell by eye. So overall, for this planet, we think that a lack of atmosphere is probably the best fit, but it's hard to get a conclusive results based on these data and the methods that we have. So this shows how imperative it is that these kinds of studies use multiple independent reduction pipelines, preferably with at least 2 visits by JWST, and use multiple statistical tests to check the fitness of the data with different atmospheric models. So overall, our conclusions thus far for GEO 1981 are consistent with our expectations, more or less, for the targets that we see relative to the cosmic shoreline, where we have kind of flatter lines and less atmospheric or fewer indications of atmosphere for our targets that are more that are expected to be drier or have fewer atmosphere or less atmosphere. And then we might have detected water for one of our kind of borderline planets. 1132b is still a little, we're still a little uncertain. And then so we'll see what we learn from TRAPPIST-1H, and we'll get those observations in November and December.
Wait, what's the smiley face?
Oh, we would give an edge to the water-rich atmosphere. We think based on our data that
The one that might
Yeah,
be the spot content.
it's not definitive, but we may have detected the water atmosphere. So maybe it's like a half smile.
Okay.
But
One eyebrow is.
a suspicious smile.
Is it just a coincidence of the timing that the ones below the shoreline got the surfers?
Yes, that was just a function of the observability and the schedule.
These other planets will be done too, the ones that are light blue and
Yes, those are in other programs. I don't remember which ones.
what's the one that's purple at the top?
So the color really just indicates the signal to noise to detect carbon dioxide. Relative to LTT 1445
Okay,
AB.
so the one that's kind of lavender, but it's well above the cosmic shoreline, which planet is that?
I don't remember off the top of my head. So I'd have to go check. But I
Kind of
think,
stands alone there.
yes, I am.
It's really cold.
Huh?
It's really cold.
Is it K218? Yes.
Maybe. I don't know off the top of my
Yeah.
head. I'd have to go check.
Interesting.
But somebody else is observing that one. It's probably K218. I know that there's a lot of excitement
Yeah.
over that one right now. Okay, so thus far from our JWST observing program, we have a few conclusions. One being that we need broad wavelength coverage of our M4 planets so that we can distinguish the planetary signal from the transit light source effect. And we really need more visits in both transits and eclipses to really understand the full context of our measurements and the spectra that we get from them. And ideally, we would get a large, on the order of a few hundred hours of JWST time to observe enough planets in enough detail to chart that cosmic shoreline for M-dwarf planets. So that's the JWST observing program. We also have our CHAMPS ICAR, which is focused on M-dwarf planets and studying the stellar spectra that we can expect from different classes and ages of M-dwarfs and their interactions with their planets' atmospheres and what we would expect to be able to observe from those planets. Whether we think those planets can support life, that based on the stellar spectrum and how that atmosphere evolves, and how detectable any biosignatures from that life. So, in summary, Dragonfly will collect in situ measurements of an ocean world that has an abundance of organic material. And from those data, we hope to constrain the processes and timelines required for the prebiotic chemistry, and better understand what makes a given world habitable. And from our exoplanet statistics and more detailed atmospheric observations that we're starting to get, we want to be able to estimate the probability of a planet being habitable, as well as constrain the best targets to investigate for habitability indicators and biosignatures. And answering these key questions in astrobiology fundamentally will require investigations on both the solar system side and the exoplanet side. So with that, I will conclude and we can do questions or chat or
Right, thank you very much, Kristin. So now we will take a little bit of time for questions in the room or on Zoom as well. So, Benjamin?
Yeah, for practical part. So you mentioned the land inside itself, crater. Is that in the inner side of the moon, say in the hemisphere looking to the planet, or the other here?
which hemisphere is it in?
Yeah,
It's just north of the equator.
right. But what hemisphere? I know this is close to 100 degrees west, so it's probably either just very, point that it points to Saturn or?
I mean, based on.
So I'm wondering whether you're looking at the planet, are you going to be able to see the planet or not?
All right, so Self Crater is here.
And the center, is the Saturnian point?
Well, I mean, the Titan rotates, so that's.
Yeah, you're locked, so you're.
Oh, yeah, I think that's roughly the sub-Saturnian.
Okay, so you will not, you will have a vision of the planet over time.
I think so.
The important question is then, do you have a camera that looks up? So you can-
No,
So Saturn.
we don't have a camera
No,
that.
cool.
looks
Right,
up.
yeah,
Saturn,
I'm just
yeah.
wondering whether you will have.
No, I think it's actually gonna be really hard for us to get a cool picture of Saturn from Dragonfly, which makes me sad.
Saturn on the horizon, could you imagine?
Maybe we could, yeah, because the forward cameras are pointed like out, and then we have the side cameras, and then we have the down cameras, so. So yeah,
You can't see the rings very well from Titan or Max. Yeah.
My question is kind of related to that. What redundancies does Dragonfly have? So to say it has a rough impact, what happens?
So, I mean, we have, as far as when you say rough impact, you mean a rough landing?
Yeah.
So, I mean, we have algorithms that are looking for, trying to detect rocks over a certain size. Somebody on the program jokes about the 25 centimeter NASA standard rock. So we're trying, but basically the algorithms will evaluate the, boulderiness of the area and try to land in a place that's less, that has fewer rocks and boulders. As far as redundancy, because Dragonfly is mass constrained, we have a selective redundancy approach. So not all of our systems are redundant, but basically if it keeps us in the air, or keeps us, or controls the power and essentially the vital systems of the lander, then we have redundant systems.
I had a question about Self Crater. How sure are we that it's a crater?
I mean, based on the topography, you can see it's pretty crater shaped. There's, a pretty deep hole and, then a rim, and something in the ejecta field. So, yeah, there are a few structures on Titan that we're based on the radar topography and the imagery. We're pretty confident there. So there are a few others that, like, well, that's kind of circular. But like Self, Minerva, Sinlat, we're pretty sure that they're.
We'll take one question from Zoom, then move to Jonathan. So there was a question from Zoom. Great talk. I have from Nicholas Scarsdale. Great talk. I have a question about Dragonfly's navigational system with no orbiter and presumably no GPS. How does it find its way around? Does it rely on landmarks, or does it just have a high enough quality map programmed in it?
So for the initial landing, it will be the landing orientation estimate will be based on our telemetry, and we have an onboard IMU, inertial measurement unit, which is more or less a collection of accelerometers that tell us our orientation. And then from there we will use the imagery from the cameras in conjunction with the IMU data to kind of know where we are and where we're headed.
I think Jonathan, and then
I was wondering how it knows where the Earth is to send data back, and kind of how precisely does it know where the Earth is in the sky, and how does it figure that out?
Well, we know that we need to be pointed southish to be able to see the Earth. So, and the beam on the high gain antenna is fairly wide. I forget exactly how wide, but it covers a decent fraction of the sky. And we also have medium and low gain antennas. Which don't necessarily help with triangulation, but would allow for some kind of communication at low data rates. And the high gain antenna will also have a search, it's gimbal, so it can have a search, it'll have a search capability where it can scan the sky to look for signal. From Earth, yeah. I mean, if we get signal from somewhere on Titan, like mission accomplished.
Noémie?
Hi.
Let's do
Is there any possibility to get below the surface organic compounds? Because if you look for terreality, for example, the one that stay at the surface, they're exposed. So like maybe below a bit or like, a few centimeters, you see what's, below the surface.
Yeah, we could use the rotors to kind of clear an area of the surface if we wanted. But the reach for the drill is probably going to be more the limiting factor for.
Like even a few centimeters.
I mean, the drill can go down. I think it's required to be able to go down something like 10 centimeters.
Okay, so you will have access to this. Oh, okay. Oh.
Yeah.
Rena, you had a question?
Yeah, could you describe the Schumann, the resonance that you were talking about to get the ice sheltedness?
Right, so the Schumann resonance, it's a little, let me see if I can back up, I don't know. It's a bit speculative whether it was detected on Titan, because on Earth, we would detect the Schumann resonance from lightning. And basically what it causes is, I forget exactly what frequency, but waves that we can detect in the atmosphere that are stimulated from the lightning that bounce off the ionosphere. So, and I think we detect those with larger antennas on Earth, and again from lightning. So it's a little more speculative, but since they think that they saw it with Huygens, we want to try to look for it.
But how would that get you the ice sheltedness?
Oh, I'm sorry, because it's really the reflection between the ionosphere and the subsurface reservoir. I'm really sorry, but I actually really need to sit down for a second.
Yes, of course.